Hello everyone, welcome to our final lecture, Chapter 13, ANOVA. It's really cool that we've reached this end, and it's amazing how this journey has been. Now for this particular chapter, we are just going to look at the introduction of ANOVA. We're not going to do a further testing and things like that. But this kind of gives you an opening into the possibility of using this test in your advanced statistics class or in a thesis where you will be working on a data set. So let's start with ANOVA. What does it stand for? Well, it's really neat because ANOVA is an abbreviation for Analysis of Variance. Now we have different kinds of analysis of variance. We have it branches off into other things too. So for the sake of clarity, I want to say that we are going to talk about one-way ANOVA. Before I go into further description of this, I just want to give you a general idea of where we use this. As you know, stats is used in every field, and the purpose of this particular test is to see if is basically to compare means, okay, between three or more groups. So how does the average or the mean behave? Is it the same in different groups, or is it different from different groups? And that's the idea. So you might wonder, well, won't the means be different because they're from different groups? No. Well, here is a case where, for instance, if you are a person who's shopping for a new car, you will want to compare the gas mileage, right, of several models. And if you find the gas mileage to be the same in all the models, then you will look at a different factor to decide or make your decision, isn't it? So it is possible that you will find the same mean in different groups. So that's for a consumer, say. And if you're talking about a sociologist might be interested in knowing the amount of income a person earns, and if that varies based on their upbringing. Okay, that's a psychologist. So a sociologist also. So does the income, vary according to one's upbringing? If it's an environmentalist, then they might wonder if the average amount of pollution varies in different water bodies. So you can have this idea of comparing means between three or more groups, and for those kind of situations we use. So let's go in here. So this is a hypothesis testing method. And when I say this, you might be able to make a quick connection with those eight-step rules, right? The 8-step process. So that is your hypothesis testing. So please remember that. And we are here looking to compare three or more means. If you are talking about one mean, you could use the hypothesis test for one population. Use the test. Remember the t-test. Now, if you're looking for two means, we didn't look at that particular chapter, but there is a way to work with two means from two different populations. And so you could do independent t-test, or we could do matched pair t-test. So there are other ways to handle if you have two means. So ANOVA here is particularly useful if you're comparing three or more means. And of course you want to see if there is a statistical difference. When I say statistical difference, I mean statistically significant difference. Among the three or more means. call it one way, right? Because we are testing one effect, effect of one factor, okay? We are testing the effect of one factor or one variable. So a factor, when we say a factor, it's a variable. In particular, it's an independent variable. And the means, right, that you're finding, those would become our dependent variables. So there is one independent variable for a one-way ANOVA, and the means become dependent variables. So when I spoke about a consumer, trying to buy a new car, does the average gas mileage of cars depend on the type of car? Type of car is the independent variable, right? The model. And you are trying to look at various mileages from the cars. Okay. I'll give you an example here of where you will use ANOVA. Now, if a researcher wants to determine, if the mean time for pain relief medications to take effect are the same for medications A, B, and C, then we want to know if that's true or if the mean effect time is different. Okay, so the mean time for the pain relief medications to take effect are the same or not. Now, because you have three groups here, medications A, B, and C, ANOVA test is the appropriate one, okay? And I'll just say it's appropriate. And if you were to, because this is a hypothesis test, we will just try to see if we can write H0 and H1. H0 would be that all these means are the same, okay? Mean time of medication, the mean time for pain relief medication to take effect for medication A is the same as the mean time for B, is the same as mean time for C. That's what we're saying. We're saying doesn't matter if it's A, B, or C, it takes the same mean time for pain relief to take effect. Okay. Now, if it is H1, we'll say at least one mean is different. Now, in order to conduct an ANOVA test, there are 6 steps. It is very similar to the other testing of hypothesis, those 8 steps, but we have 6 steps here. Okay. So step 1 is to confirm or check requirements, because if the requirements don't meet, you cannot use this test. 2, determine degrees of freedom. Then it kind of follows things we know. Determine the critical value and rejection region. Is to compute the test statistic. 5, construct ANOVA table to summarize the analysis. 6 is to make the decision for the test and interpret results. So out of these, we will be looking at this and this, the first 2 steps. So let's start with the first one, the requirements. How do we confirm the requirements? What are these requirements? So we actually have some strong requirements for a one-way hypothesis test. One way, I should say, ANOVA hypothesis. Okay, first one is that each population from which a sample is taken is assumed to be normal. Then all samples are randomly selected and independent. You can think about this. We're talking about 3 or more means. That means they're coming from, obviously, 3 or more populations. So for each population from which a sample is taken, we want them to be normal. So we want the background populations, whichever group you're taking from, they are populations to all be normal. Okay? That way, this test is robust. Otherwise, you can't perform this test. Then those samples must be randomly selected, of course, to keep the to remove any bias, and must be independent. The populations are assumed to have equal standard deviations of the analysis. You know, standard deviation, when you square it, you get variance. That's why we say or variances. For the factor, remember factor is the independent variable. That must be a categorical variable. Categorical is qualitative. Is a categorical. So categorical, like medication A, medication B, medication C, right? You are not giving a number, so you're talking about the quality, not the numerical value. So I just say qualitative. The response variable, numerical variable, which is qualitative. Quantitative. So if you have all these 5 conditions satisfied, then you're done with step 1. And then you can move on to step 2 and through step 6 to finish the testing. So what we generally do is, when we have an ANOVA null hypothesis, you know, null hypothesis always has the equals. So your H0 will always be the means set equal to each other. We don't know what these means are, right? If it's ABC, then you do ABC. It's 1, 2, 3. we're just trying to say, well, you can have only a finite number of such means that you're comparing. So it's all the way up to mu k. K is some finite number. Now, in our example before, your k was 3, right, in that medication problem here. That's why k was 3, so you just had 3 of them, mu a, b, and mu c. So the 3 of them were set equal to each other. And the alternative hypothesis, is of course H1, and it has the inequality. So we say at least 2 of the group means are not equal. The fact that at least one of them is not equal would actually hold true, right? If one of them is not equal to another, then that affects your H0. That's why we say at least 2 of them are not equal, right? Because you need one to compare with the other. So at least 2 of the group means. So if you reject your null hypothesis, then you can conclude that at least one mean is different from the other means, right? Or at least 2 of them are different. One is different from the other means. That's what you can say. But then you only know that one of them is different. We just don't know which one it is. We'll know at least one of them is different. And we do have, of course, additional tests that will help us to deal with that. Here is our next example. We will look at first one here. A doctor wants to determine if the average amount of time needed to eliminate a muscle ache is different for aspirin versus acetaminophen versus a placebo. The doctor randomly selects patients for a study and divides them into 3 groups, where each group will be administered the different medications of aspirin, acetaminophen, and placebo. Assume the populations are normally distributed and have equal variances. Now, if even if we wanted to use ANOVA, the first hurdle is that all those 5 conditions must be satisfied. So that's what we're trying to do here. Okay. So we'll start with the condition number 1. If you come back here, condition 1 says each population from which a sample is taken is assumed to be normal. So we'll see, is that condition met? The populations are normally distributed. That's good. So we know that normal distribution is assured. The question already tells us that they assume that these are coming from normal distributions. 2. All samples are randomly selected and independent. Now these are samples of patients, right? And it says the doctor randomly selects patients for a study and divides them into 3 groups. Okay, so we have, what do we say? Condition 2, which is random samples. I'll just put it in shortcut, okay? Random samples and independent. So they are divided into 3 groups, so you don't have the same information, the same patient in 2 groups at the same time. That cannot be. They will be in 1 group only. So the independence is established. That is what we mean here, right? So the same individual cannot be in more than 1 group. That will make it dependent. So they're all independent. Okay, and third condition, the populations are assumed to have equal variances. Yes, equal variances. That information is down here. Okay. We are told that these are coming from normally distributed populations and they have equal variances. So the third condition is good. Fourth condition is the factor must be categorical. Okay. So what is the factor here in this example? In this example, your factor is the type of medication that is used, right, to eliminate muscle ache. So each group will be administered different medications, right? So factor is the type of medication. Being used to eliminate muscle ache. So it's type of medication, which means aspirin, acetaminophen, placebo. These are all qualitative, right? So it's categorical. So this is a categorical data. And our fifth condition is that the response variable, the dependent variable, is a numerical variable. So our response variable here is the average amount of time needed, right? So that is a numerical because you can measure the average amount of time. So I'll just say here, response variable would be the time needed to eliminate. So that will be a numerical variable. Here I said categorical data. That should be a categorical variable. Alright, so we got all those 5 conditions. Because the 5 conditions are satisfied, we can go ahead and use ANOVA testing of hypothesis to work on this problem. But for now, the question just wants to determine if this can be done, and for that we tested the 5 conditions. Here's the next problem. An accounting firm is planning to set up a one-way ANOVA hypothesis test to determine if the average sales amount for salespeople in branch 1, branch 2, branch 3 and branch 4 are the same. Assume the populations of each branch are normal, the population variances of each branch are equal, and that the samples from each branch are equal. Write the null and alternative hypothesis for this ANOVA test. Well, they want us to write the null and alternative hypotheses, but even for that we need to test all the 5 conditions. Okay. Now, thankfully, they did give us these conditions very quickly here. So that's normal distribution, right? All the populations are normal distribution, and we are told that the samples are randomly selected and independent. That's condition number 2. The populations are with equal variance or standard deviation. The population variances of the branches are equal, so that's the 3rd condition. The factor is categorical and the response is numerical. So come back here. What is the factor? Okay, the factor is the branch type, right? So I'll just write here somewhere. Branch type, okay, which is categorical, branch 1, branch 2, and the response variable must be numerical, which is to determine if the sales amount that can be measured, right? So I can call it as B1, B2, branch 1, branch 2, branch 4, right? Branch types. And this is sales amount, so it must be in dollars. Okay, so now we're ready to write. We just tested the five conditions, but the actual question wants us to write H0 and H1. So we have mu of branch 1, the mean. What is the mean? Mean here is the average, right? That's how you know it's the mean. So it's the average sales amount, or the mean sales amount for salespeople in branch 1. Okay, so that's the mean amount from branch 1 is the same as branch 2. Is the mean amount is the same mean amount in branch 3 and branch 4. And then H1 says at least one of the means is different, okay, or at least two of them are not the same. At least one of the means is different. And they just asked for these two and we answered those two. Now we talk about degrees of freedom. Now we know about degrees of freedom. We've used it in the t-test. Here it's slightly different. Okay, in order to understand the degrees of freedom, how it works here, we have to understand what distribution this is. For ANOVA, we use a new distribution. Okay, it's called the F distribution. Okay, F here stands for Fisher. Okay, actually it is Sir Ronald Fisher, an English statistician who came up with this, and so it's named in his honor. And also it is interesting that it's F because it's a fraction. Okay, this F distribution appears as a fraction, so the statistic is a ratio. In particular, what is this ratio? This ratio is the ratio of the variability between groups to the variability within groups. So you can say F is the variability, right? That's the variance between groups over variability within groups. So the variability between groups is between A, B, C groups. And if it's within groups, within A is the variability, within B is the variability. And so what we're saying is, what this helps us to do is, it helps us to first find if there is only a minimal difference between the means. If that's the case, then we would expect that between the group variability and the between group variability and the within group variability, they would be approximately the same, right? If the means weren't so different, then their variability up and down won't be so different, in which case the F statistic will be close to 1. If that's the case, okay, if that's the case, then we can say that minimal difference in the means. Okay, so you can actually say that it's in other words, you can say H0 is true, right? If there is no difference in the means. But if your F has to be always positive, so if this is greater than 1, then we have evidence to conclude that at least one of the means is different. If F is greater than 1, it implies at least 1. And so that is where we use the statistical test to see if that difference is significant. So when we talk about when we talk about the F distribution itself and we indicate it, remember for chi-squared we had chi-squared with the degrees of freedom. I'm going to remove this, but if you recall, we said chi follows a chi-squared distribution with degrees of freedom in the bottom. Yeah? Likewise, here you have F that follows an F distribution with degrees of freedom from the numerator and degrees of freedom from the denominator, because you have the numerator and denominator is a ratio of variability. You'll have degrees of freedom from the top and degrees of freedom from the bottom. That is what makes this different from every other distribution we've seen, because all other distributions had just one degree of freedom. Here you have a degree of freedom for the numerator and degree of freedom for the denominator. So if I say F follows a F distribution 4, 10, then this means that this 4 is the degrees of freedom for numerator and 10 is the degrees of freedom for denominator. And what is the formula for that? So the degrees of freedom for numerator. So just for our understanding, I'm going to say df with a nr as a suffix. Okay. The formula is k minus 1, okay, where k is the number of groups. I'll just write it in notes. Is the number of groups. The degrees of freedom for the denominator df with a dr suffix. That is capital N minus k, okay, where n is the sum of the sample sizes for each of the groups. Now in the following examples, we will find the degrees of freedom for the numerator and the denominator. So our problem here says, a company president is planning to conduct an ANOVA hypothesis test to determine if the mean overtime for companies A, B, C, and D are statistically the same. Random independent samples are taken of employees in each of the 4 companies as shown in the table below. Determine the degrees of freedom for the numerator and determine degrees of freedom for the denominator. Okay, for this problem, let's assume that the 5 conditions were met, and so we now go on to finding the degrees of freedom. So degrees of freedom for the numerator, the formula was k minus 1. So you have to see how many groups there are. And we are told that there are 4 companies, 4 groups, right? Company A, B, C, and D. So K is 4. 4 minus 1 is 3. And then the degrees of freedom for the denominator is given to be capital N minus K. So we need to find capital N. It is the sum of the sample sizes for each of the groups, right? So if you see that the title of the second column says number of employees taken as a random sample. So this is the sample size for the first group, right? So 15. This is the sample size for the second group, sample size for the third group, and for the fourth is 20. Add them up. So if you add them all, 15 plus 18 plus 10 plus 20, we get 63. So that makes it 63 minus K was 4. We used that previously, right? 63 minus 4 is 59. So we will need these two to perform the test. So we found the degrees of freedom for the numerator and the denominator. Our next problem says A research company is conducting a study to determine if the average monthly internet bill is statistically the same for 3 internet carriers, carrier A, B, and C. To collect data for this ANOVA test, the research company randomly selects customers for the 3 internet carriers and records the amount of the monthly internet bills for each customer as shown in the table. When conducting this ANOVA test, what is the corresponding degrees of freedom for the numerator and the degrees of freedom for the denominator? Okay. So again, let's assume that the 5 conditions are met. But just for our understanding, I just want to discuss about the factor and the response variables. The factor here would be the independent variable, and the independent variable is the carrier type, the different carrier types, right? So that will be an independent variable. And our dependent variable, right, would be the amount of the monthly internet bills, because that's the dollar value and that is numerical and that's also entered. Okay. All right, now let's get to the problem. So degrees of freedom for the numerator is k minus 1. Okay. K is 3 groups, 3 carriers. So 3 minus 1, which is 2. And then the degrees of freedom for the denominator is capital N minus k. Capital N is that we have to count all of these, right? How many entries we have. So because it's that many entries that counts for the sample size. So you could do it in many ways. You could add the columns one by one and add all the 3 columns in the end. Or you could just count them. So 1, 2, 3, 4, 5, 6, 7. 7. 1, 2, 3. 7 times 3 is 21, and there's one more, so 22. 22 minus 3, which is 19. So we found the degrees of freedom for the numerator and the denominator for this problem as well. We said F distribution is a ratio, but how does the distribution look, right? So we would be curious to see how it looks. Well, what we notice is that the F distribution is a family of curves, right? And the curves are defined by the degrees of freedom for the numerator and the degrees of freedom for the denominator. That's why we just found all those things. So F curve is defined by df of numerator and df of the denominator. And when we talk about the distribution, we say degrees. We indicate the F distribution by its degree of the numerator and denominator. So in the previous example, we found the degree of the numerator to be 2 and the degree of the denominator to be 19. In that case, it would be written like this, 2, 19. So we understand that. And then, as always, the area, the total area under the curve the F curve is always equal to that's interesting. No matter what the shape is, it's always going to be equal to 1. And the F distribution curves are also skewed to the right. Okay, and the F values are always greater than or equal to 0. Like the Z values, the T values, your F values are also, just like the chi-square, I should say, F values are greater than or equal to 0. Or equal to 0. Now note that your chi-square and F only are allowing values to be greater than or equal to 0. But your T-test, Z-test, these were all fine with taking negative values, right? Your Z-scores went in the negatives, and usually it was as low as negative 3.5, and it went as high as positive 3.5, but it could technically be any negative or positive number. And for chi-squared and F, what we're seeing is that it has to be only on the positive side. So the graph would look very much like your chi-squared. Okay. So it's happening only on the positive. And then depending on the degrees of freedom, right, your curve can look like any of these. Like the pink one, okay? The pink one would be f with 1 and 1,5, which means the degrees of freedom for the numerator is 1 and the degree of freedom for the denominator is 5, right? And then if you had something like that, it could probably go down. The blue one would be f 5,10. So you can see that with a little more degrees of freedom, you are able to get the curve beginning to look more like bell shape, but it's still not sufficient. For it to look bell shape, remember that your degrees of freedom, the numerator and denominator, must be large and close to each other. So you will notice that this is how the graph looks for f 100, 100. And of course this kind of stretches further on. On the left end it stops at 10, but at 0, right? It starts at 0, I should say. So it doesn't go beyond 0. But on the right it extends indefinitely. And then of course once we know the level of significance, we will use that to find the f statistic. Just like the chi-squared, we also use the f table. The f table, a portion of the f table looks like this. As you can see, the degrees of freedom for the numerator is given here, right? So this will be your df numerator, and this is the degrees of freedom for the denominator. So if we give you some specific values, you can find the corresponding f statistic. So for instance, this is for alpha 0.05, right? So for each alpha, popular alpha of course, we'll have different tables. So for this one, let's say you are asked to find for f, we saw one of them, right? 5,10, let's use that. 5,10 for alpha 0.05. So 5,10, 5 is the degree of the numerator, okay? So the numerator is 5, come down all the way up to 10, and then you have it as 3.33. The f statistic is 3.33. Okay. And of course, we're not doing the test. I just wanted to give you a glimpse of how this table would look, and you will use this to proceed further with the testing of hypotheses. So, well then, with this, we come to the end of chapter 13, okay? And all I wanted you to pay attention to here was to understand the 5 conditions and to be able to determine the degrees of freedom. Okay? I hope you enjoyed this kind of comparatively short lecture, a nice way to end our series. And I really am thrilled that we've come to the end of this course, but I'm so glad that our journey was beautiful all along, and I thank you for being great students. All right, see you later. Bye-bye.